I'd like for this video to serve as something of a consolidation of a couple derivative-based problems. But before we actually get to it, I think it's useful to at least elaborate on or regarding what the derivative actually is, right? So the derivative is really the slope of the tangent line at a particular point. So, if we had a line in particular, or actually if we had a function, the idea of the derivative is like if I had an x value here, then at this particular x value, really what is the slope of the line that is tangent to that point? So that essentially that inclination or a measure of that inclination is what one would call the slope of the tangent line, right? It's a tangent line to a function, and the extent to which it is steep or unsteep is really what we would call the slope. And this has another interpretation, or at least another definition, as being y2 minus y1 over x2 minus x1, which is just really 2 points on the particular tangent line. And if we take these 2 points, and we would also have maybe x1 here, or we can call this one x1 and this one x2, and we'll call this one y1 and this one y2. So it's the difference, right? The change is the difference. So what you would do is you would minus the distance elapsed in x, and you'd minus the distance elapsed in y, and so you do y2 minus y1 over x2 minus x1, and you would get the slope. So the idea is that the slope, or also regarded as m when we're looking at the point slope formula, or if you see the standard form y equals mx plus b, this m in particular is responsible for the slope, which is the derivative, which is the tangent line, or the slope of the tangent line at a particular point. So m is in fact y2 minus y1 over x2 minus x1, which is rise over run, which is also the derivative of f prime. So the derivative just means, in essence, it just means that it's the slope of the tangent line at a point. The extent to which that tangent line slopes is, in fact, the derivative. So we're going to work on a couple questions, and we'll try to consolidate what we've learned regarding derivatives and different questions and their applications. Our first question here is to sketch the graph of the derivative. Now, the basic idea, and perhaps we'll look at a side example, is that if we had a graph like, let's say something like this, right? Essentially, we would have a parallel graph to this, and we would have it look something like this. And this would be, this would be f of x, this would be f prime of x. And the basic idea here is that we want to first draw out, and let me go ahead and zoom in here. We want to first draw out where the slope of the tangent line at a particular point is 0. So in this case, if you draw a slope of the tangent line here, in this case, it would be 0. And in this case, it would be 0, because the tangent lines at those points are completely straight. And if you think about the inclination of a line at those points, or the horizontal line that is, it has no gradient, right? It doesn't have an inclination. It's not steep or unsteep. It's just completely straight. So it doesn't really have a slope per se. Or it does have a slope, but the slope is 0. So at this point, m is equal to 0. And at this point, m is also equal to 0. And so we want to sort of reflect that fact here on the other graph. And we'll put a point here, and we'll put a point here, because this point as well also has a tangent line of 0. And actually, let's get that perhaps to be a little more straight. And so at this point, what we'd like to do is we want to think of these points as being separating regions, right? So this, everything to the right of it is, or the left of this point is a region. Everything to the right is a region. This is also a region, and this is also a region. So what we're doing in this case is we're looking at, okay, we're looking at the graph, and we're seeing that, from this point of view, the graph is actually the slopes of the tangent line at these points before it gets to m equals 0 is positive. So those tangent lines are positive. And why we're separating these regions off is because we know that at m equals 0, the function is going to do something different. That's a point of change. And so, it's definitely going to be either positive or negative on one side and then either positive or negative on the other side. And so we're just separating these off and seeing what the slopes of the tangent lines are in each region. Because if I were to, and then we would get an idea of how to draw the graph. So, all these tangent lines here are positive. I could draw any tangent line because you want to remember, you want to recall that, that anything of this form or, of this form, this is positive sloped, and anything of this form, like if you're going downwards, like this is negative sloped. So we want to recall that idea here. And of course, this line matches this particular graph. So we're going to say that's a positive slope. And so if it's positive, it shouldn't be down here in this region. It should, in fact, in this region at least, it should be positive. So it should be above the x-axis. So we're going to say it's going to be in this region, somewhere in this region. And so as we move on to the next region, we see that the tangent lines, I could draw a tangent line at any point into the next region, and those tangent lines would in fact be negative. So I'd want in this region at least to have, I'd want to have the tangent line represented as a negative number. So I'd want to be here. So if it's positive, you're above the x-axis in that region. If it's negative, you're below the x-axis in that region. And so as we move on to the next region here, we reach 0, and then the tangent line it's going upwards, right? So we should be we should be here, because here it's negative, and we took into account that fact, and then it continues being negative, and then it eventually becomes positive, right? Because the tangent lines at this point, they're all positive. So we'll say that these are all positive. And correspondingly, we'll then say that, this should be above, it should be above the x-axis. And now it's just a matter of drawing lines that pass through these regions, right? So we said that it was positive here, so it's going to start here, and then it's going to go down, and then it's going to go up. And then it'll continue on that way. So this is f prime of x, this here is f of x, and so here it's positive, here it's negative, and here it's positive again. And so we'll replicate that idea here. What we will do in this case is we'll actually draw another graph. And what we will say is that, we know for a fact that at this point, there's like an inflection, there's a point where the gradient is 0. And so what we'll do in this case is we'll say that we'll put this point at 0 here, because if the slope is 0, then it's going to be right on the 0 line, or at that point 0 on the x-axis. And what we notice on this side, or this side of the graph, or of that point, the slopes of the tangent lines are actually, they're all negative. So we're going to represent that fact as, we're going to be in this part of the graph, and And then as we pass through this point where m equals 0, all those tangent lines are then positive. So we're then going to sort of be in this part of the graph. And so we're then going to say that, it's negative at first and then it's positive. And that would look something like this. So this is y, and this would be y prime of x. And that would essentially be our derivative. So in this particular case here, it's essentially saying that a rechargeable battery is plugged into a charger. The graph shows C of t, the percentage of full capacity that the battery reaches as a function of time elapsed in hours. And so for part A, it's asking what is the meaning of the derivative C of t? And then for part B, it says sketch the graph of C of t. What does that tell you? So we'll essentially tackle on A first. And for part A, well, what does the meaning of the derivative C of t tell you in the context of percentage and hours, right? So if we were to, and of course we're recalling that the derivative means the slope of the tangent line at a particular point, that's just the rate of change, the instantaneous rate of change. So if I were to, pick a point here at let's say 4 and then draw sort of a tangent line at that point, this is the slope, right? And we know that the slope is like, the derivative, right? But what does it mean, right? It means the instantaneous rate of change. So m equals, we'll say that m, or the slope, is the instantaneous rate of change. And actually, I think we'll mention that in the question down here. But it's the instantaneous rate of change. So it's actually telling us with a particular input of hours to what extent is the percentage charge changing with respect to time at a particular instant. And that at a particular instant part is so important because it's telling you that it's the derivative. It's the instantaneous rate of change. It's not the average rate of change. It's the instantaneous rate of change at a particular instant. So the idea here is that, what is the rate of change at a particular instant with respect to two variables? Here, we kind of have two variables. We have the percentage of full charge and we have the hours. So what is the rate of change of percentage with respect to time at a particular instance? So we'll say that since the derivative represents the instantaneous rate of change, the slopes of the tangent line at any given value of x, f of x, which is just a particular coordinate point, signifies the rate of change of battery, or we can say percentage charge, with a particular input of hours at a given instance, or at a given instance. So the derivative, since the derivative represents the instantaneous rate of change, the slopes of the tangent line at any given point, at any given value of x, f of x, signifies the rate of change of percentage charge with a particular input of hours at a given instance. So that's the idea. And that just alludes to what it means to take the derivative of something, right? Now, part B is slightly more taxing, I would say. First, it says to sketch the graph of C of t, or so this is the graph of C of t, right? So this is C of t. This is the graph of C of t. But if we wanted to sketch the graph of the derivative of C of t, which is C prime of t, we would actually have a So we would have a graph. And the idea here is that, and actually let's get that tangent line in. The idea is that, what we notice is that at this particular, so if we're looking at if we're starting from the origin, right, the tangent lines at those points are positive, and we know that it's positive because anything fitting this form is positive. So the tangent lines at those points are in fact positive. And then as we, the tangent lines at those points, they essentially get less positive. They're decreasing, and they're not going negative, but they're essentially less. They're less positive, right? So essentially, as you so you're starting very, very positive, and then as you proceed down the graph, you're getting less positive, and you're almost approaching zero, because your slope, that is almost approaching zero, because your gradient is almost becoming a straight line. So you could say that your derivative or your slope or your gradient, all three of these things mean the same thing. But you could say that your gradient is getting closer to zero. So you start at a very high positive number because you're just representing the quantity of your slope. So it's starting very high, and you can tell that because your slopes are positive. So it's starting at a very high value. And as you continue, the positivity decreases because the slopes of the tangent line decrease in the sense that they're less steep as the graph moves forward. And so being less steep implies lesser positivity, if that makes sense. And so that positivity gradually decreases and then gets closer to zero. And so this would be the graph of C prime of t, right? And then as for what the sketch of C of t, what does the graph tell you? Well, it tells you that at an initial point in time, for at zero and then onwards, it's very positive, which means the rate of change is positive, and it slows down as time elapses. So as you're moving forward, as that percentage charge is increasing, we can see the rate of change decreases, in the sense that the rate at which the battery charges decreases. So you could say the graph of C prime of t tells us that initially, at several instances, the rate of change is positive in terms of magnitude, and as time elapses, for those instances, the rate of change regarding charge approaches zero, implying that eventually the rate of change will be zero, rate of change may be zero, and the charge, because charge may not be needed. So the graph of C of t tells us that initially, at several instances, the rate of change regarding charge is positive in terms of magnitude, and as time elapses, for those instances, the rate of change regarding charge, we'll just say, decreases and approaches zero, because after a particular time, no charge may be needed. So initially, percentage change in charge with respect to time increases at a fast rate, decreasing as the percentage charge increases with respect to time, eventually approaching zero change because charge may not be needed. And that should summarize, I would say, this question. I think what we'll do in this case is we'll try to put B next to A in some sense. And that should summarize C of T. C prime of T, rather. And this is, again, section 2.8. So this particular question tells us to find the derivative and state the domain. So if you're not familiar with what the domain actually is, the domain is actually just it's essentially like if you have a function, right? So you're looking at a function and perhaps we'll say that at this point, right? At this point, there is a hole. Right, so there's a point on the graph where there's a hole. So the domain, you can think of the domain as being, the domain is defined as being all the valid inputs of X that yield a corresponding definitive Y value. So, if you think about it, I can put if I input, let's say this is 4, if I input 4 into my function, I can essentially have a definitive Y value or corresponding Y value here, and that would make up an ordered pair. So I'd have 4, and then if this were, let's say 5, I'd have 4, 5. And if, and I could do that for every single point along this particular curve. But the idea is that, as I approach X, I can't do that for an input here because, there really isn't any, X value that I could put there and get a defined corresponding Y value, right? Because there's a hole. So the idea is that, if you're looking at this graph, what you would say is that, the domain for this function is from infinity, because I can still put everything to the right, or to the left rather, and I can still put everything, but as I approach X, so I can do everything infinity to X, right? So to this point, I can put any point and it would work. And then I can do any point after. So I'll do union X comma negative infinity. Oh, sorry, do I have that backwards? So this is positive infinity, this is negative infinity. So negative infinity to X, union X to infinity. Now you may be asking, so the basic idea here is that, I can put in any X value to the right of X or to the left of X and still get a definitive corresponding Y value. And I can do the same thing for the left, or basically on the right and the left of X, I can input X values and get a definitive Y value. But at X, I have a problem because I can't put an input of X there and get a definitive Y value back. So I say that the domain is from negative infinity to X, and then from X to infinity. And then the fact that I've included a closed bracket means that I'm not actually including X. So if I put, closed brackets near X, that would mean that, my domain is from negative infinity to x, also including x, and then from x to infinity, so also including x. So I don't actually want to include x in the domain because x isn't a valid input that would give me a corresponding y value, so I just leave it at that. So the domain is just defined as being all the valid inputs of x that yield a corresponding definitive y value. I don't have that definition met at x at an input of x, right? So that's the domain. One thing to remember for polynomial functions, the domain is all real values in the sense that, polynomial functions, they're continuous everywhere, right? So they're not actually going to have any holes or breaks. So I wouldn't actually have any values where I could input an x and I won't get a corresponding y value back. That's just not going to happen for polynomials or linear functions. But the idea is that it's not really asking you to find the domain of the function. It's actually asking you to find the domain of the derivative of the function. And at this point, it wants you to use the limit definition of the derivative. So we're going to go ahead and do this on the side here. So we're going to say that the limit as, or f prime, f of t prime, which is the version of this function, but this is just the derivative. F of t prime is equal to the limit as h approaches 0 of f of t plus h minus f of t over h. And we essentially have established at this point that f of t plus, so essentially what we want to do when we're looking at f of t plus h is we want to actually take t plus h and then plug it everywhere we see a t in the original function. So you can go off to the side and do this. You can say that, f of t plus h, it's just telling you take t plus h and plug it back into the original function everywhere there's a t. So f of t plus h is going to be t plus h cubed, right? T plus h cubed minus 5, and then t plus h plus 1, right? And then we already know what f of t is, right? F of t is just what we were given in the question. So f of t is just t cubed minus 5t plus 1. So t cubed minus 5t plus 1. And then at that point, it's just a matter of, plugging into this formula. So we'll say that, the limit as h approaches 0 is essentially going to be t plus h cubed minus 5t plus h plus 1, and then over h. And actually, this was only f of t plus h, right? But we actually want to extend this further and do minus f of t. So we're going to do minus t cubed minus 5t plus 1. You actually want that that bracket there because what's going to end up happening is all these are going to end up interfacing with this negative, and so you want to ensure that you're taking into account that fact. So essentially, the idea is that if you have a plus b, right, minus x, and x is equal to z plus d, you don't just want to put, you don't just want to put z plus d here. You don't just want to put z plus d. You want to put z plus d because eventually what's going to happen is that this negative is going to distribute and actually make z plus dz minus d. So that's the basic idea, algebraically at least, on how to do that. So just moving forward with our calculation here, the limit as h approaches 0. So t plus h cubed, right? We're definitely going to have to distribute that. And, you could go about it several ways. Perhaps you could do t plus h cubed is t plus h, and then again you have a t plus h, and then again you have a t plus h. But let's first start by just distributing the t plus h's first. So we'll say that this is t squared plus th plus ht plus h squared, and then you'll have t squared plus so this would, th and ht are actually the same thing, and so it's just 2th plus h squared. And then what you're going to do, because you had a cube here, you would do t plus h, and then you're actually going to do t squared plus 2th plus h squared, and then you're going to distribute. So you want to do this first, and then go ahead and do this, right? So, first just doing this here, that's t cubed plus 2t squared h plus th squared plus ht squared plus 2. So we'll have plus 2. Actually, so we did t cubed and then 2t squared h and then plus th squared. I think it'd be better if I did that as th squared instead of, so t cubed and then 2t squared h and then th squared. Well, t cubed and then 2t squared h and then th squared, which I already have. So now we're moving on to the h, so we'll do ht squared plus 2th squared, 2th squared, and then we have h cubed to top it all off. And the idea is that, we have this t plus h cubed. We essentially want to take everything and then put this back into the function and or the limit. But the thing is that this may get slightly long. So hopefully, luckily we can move things around here, but we'll go ahead and put this guy here. And we would obviously also want to move on and distribute -5. So -5t minus 5h, and then minus t cubed plus 5t minus 1. And this would all be over h. And you'll actually notice that the -5t's actually, they cancel out. And then, you're looking around for anything that could also cancel out. You have let's see here, I think we had a 1 here. -5t minus 5h plus 1. So there should have been a +1 here because I think we forgot to add that. So your -1 would actually cancel out with your +1. So minus t cubed plus 5t and then -1. So you're really just left with t cubed. I think these cancel out as well. And I think that's it. I think, and you'd expect to be left with only the h terms because the h terms are actually the ones that should be canceling out, because you'll eventually factor them, right? So the limit as h approaches 0 is 2t squared h plus th squared plus ht squared plus 2th squared plus h cubed over h. And we have a minus 5h here as well. And then this would just be a matter of, just factoring out everything. So we'll go ahead and grab the h because h is consistent throughout. So we'll just go ahead and say, h and then 2t squared plus th plus t squared plus 2th plus h squared minus 5 all over h. And these would cancel out, and then we're left with the limit as h approaches 0. And at this particular point, we can really just substitute because these canceled out. So we're really just left with this guy here. In other words, we're just left with everything inside. And we can essentially here, we'll actually substitute for h because there's really nothing else you can do. 2t squared plus 0, because this would, h times t would go to 0, plus t squared plus 2th, so that has an h in there, that'll go to 0, plus 0 minus 5. So we can say that this is just 2t squared plus t squared, 2t squared plus t squared minus 5, which I suppose you could just say it's 3t squared minus 5. And at this point, I believe what you could do is you could just say, this is your derivative. So f prime of x is equal to 3t squared minus 5. But this isn't actually where the question ends, because the idea is that, you want to state the domain. If you remember, the question said state the domain of the function. So essentially what you'd want to do now is, now that you have f prime, which is 3t squared minus 5, you want to state the domain. So what we'll do in this case is we'll say that the f prime of x is 3t squared minus 5, which is a continuous function because it's a polynomial. All polynomials are continuous on their domain. Hence, the domain would be negative infinity. So you could say it's negative infinity to positive infinity. And the idea behind that is that, you could take any input of x, and any input of x would essentially allow you to, well, on a polynomial function at least, would allow you to put any input of x, and you would definitely get a corresponding y value back, because there aren't any holes, jumps, or breaks anywhere. So that this is number 42, and the idea is that what it wants us to do at least is explain why the following points, or explain why certain points on the graph are not differentiable. And the basic idea behind this question is that, you have to sort of realize that, if a point is differentiable, then it must be continuous. In other words, if you think about differentiability, like like x equals a particular value, like here, for instance, I can draw, slopes to the tangent line, or I can draw a slope to the tangent line at this point, which would really look something like this, But the idea is that, if it's not continuous there, right? If there's like a, if there's like a hole where it's sort of undefined, then you can't draw slopes to the tangent line at that point, which would look something like this. You can't do that. And so, it's not differentiable. In other words, you can't take the derivative at that point. If you can't draw slopes to the tangent line, or if you can't draw a slope, if you can't draw a tangent line at that point, then it's not considered differentiable. And with undefined points, you can't. So this comes back to continuity. So I guess the first thing we could say is that for a point, we'll say that for a point to be differentiable, it must be continuous at that point, right? So we'll go ahead and say that. So for a point to be differentiable, it must be continuous at that point. And of course, if this is violated, for instance, if it wasn't continuous at that point, then it wouldn't be differentiable. And I guess you could add that as an add-on. You could say that if a point isn't continuous, then it's not differentiable, right? So just looking at some points here, you'll notice that at x equals 2, I could draw tangent lines, so it's differentiable there. But at a cusp, so this is -2, then -3, and then -4. So at -4, there's a cusp. And the idea is that if you have like a corner or a cusp or like an arc, it's the function, is continuous at that point, but it's not differentiable. You can't draw a slope to the tangent line at that point. So the reason it's not differentiable at that point is because, if we look at the absolute value function on Desmos, you're looking at this point, right? And this is the absolute value of x. F of x is equal to the absolute value of x. Well, let's actually mathematically see if we can take the derivative at that point. In other words, can we apply, so for a given function f prime of x, which is the absolute value of x, can we apply the limit definition, which is, f of x is in fact, f of x itself is the absolute value of x. And can we actually apply the limit definition here? So can we say that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x? Can we do that over h? Well, f of x plus, so what is f of x plus h? We know that f of x is the absolute value of x, so the absolute value of x plus h minus f of x, which is just the absolute value of x, over h. And of course, we're still taking a limit here. So we're still talking about a limit, that is. So we're going to say the limit as h approaches 0. Now, this would just be the limit as h approaches 0. So x and minus x would cancel out, and we're just left with h over h, which is an indeterminate, which is 0 over 0, which does not exist. So the idea is that therefore at cusps or corners, derivative dne right? So at cusps or corners, the derivative does not exist. And this was us finding the derivative, and we know that the derivative doesn't exist because we get 0 over 0, which is an indeterminate form. So at cusps or corners, the derivative does not exist. So we're going to say that at x equals, I believe that's -4, the derivative dne, because of all this, because we're looking at, something like this. So what we can then say is that, okay, at this point, it doesn't exist. And obviously at 0, it doesn't exist, right? And that's true because, it's not continuous at 0. And you can essentially say that the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. Hence, that violates a condition for continuity to be met. Therefore, and we know that for a point to be differentiable, it must be continuous at that point. Therefore, x equals 0 is not differentiable. And that would be the reasoning behind it. So this question is asking us to take the derivative of a particular function in a manner that best resembles not the type of derivatives that we're aware of, but rather it is essentially asking us to take the derivative using a different definition. So so there's like just how there were limit laws, there are also derivative laws. So the derivative, actually, let me go ahead and zoom in here a little bit. The derivative of f of x plus g of x is actually equal to the derivative of the individual functions plus the derivative of the individual functions. So g of x. And the same would be applied here, but I think it's better to cover another rule as well, which states that the derivative of a constant times a function is equal to the constant multiplied to the derivative of that function, if that makes sense. So in this case, y will equal the derivative d over dx of 3 raised to the power e to the x plus the derivative of 4 over 3 under root x. And this would essentially just be doing the y equals 3 times the derivative d over dx of e to the x plus, because of course we're pulling that constant out, sort of in obligation to this rule. And I want to also elaborate another fact that, if I have 1 over 3 to the x, this is the same thing as x to the negative 1/3. Because we know that, a to the x to the n is equal to x to the n over a, but if it's in the denominator, if you have x n over a, then that's just minus x. Oh, sorry, it's actually x minus n to the a if you bring it up to the top. So that's the reasoning there. So in this case, 3 actually plays the role of a, and n actually plays the role of 1. There's an implicit 1 here. And so when you bring that up to the top and you sort of remove the radical, you actually have to, it is 1 over x to the 1/3, but then when you bring it up to the top, it becomes negative 1/3. So we can actually say that this is the derivative of 4 multiplied to x to the 1 to the negative 1/3. And then this is just another constant rule. So this is y equals 3 times the derivative of e to the x plus 4 times the derivative, because we're pulling that constant out, of x to the negative 1/3. And so that means y, or really y prime. Y prime is, so another thing to remember is that the derivative of e to the x is actually just e to the x. So this is just 3e to the x plus 4 times the power rule. So the power rule is like x to the n. If you have x to the n, the derivative of x to the n is just n times x, n minus 1. So take that power down, you get n to the n times x, and then decrement the exponent, which is n minus 1. So that would just be negative 1/3, because we're bringing that power down, and then multiplied by x, negative 1/3 minus 1. So you could do that off to the side, negative 1/3 minus 1, which is the same thing as saying minus 3/3, is minus 4/3. So we can say that this is minus 4/3. And then this would just be 3e to the x. This minus sign is going to be pulled out. 4/3x to the negative 1/3. And then that's your final answer for this particular question. This next question actually wants you to find the slope of the tangent line. So I guess we'll make that clear here. It says to find slope of tangent line. And we used to, we used to do this, right, by using this definition. We used to find the derivative, the general derivative, by which we could plug in any value of x, and it would give us the derivative at that input of x. But in this case in particular, we're not using f prime equals, the limit as h approaches 0 of f of x plus h minus f of x over h. We're not using that definition here, although it would get us to the same answer. We're actually going to take the derivative of this polynomial. And what we would want to remember in this case is that the derivative, so we're going to find the derivative in another way, and that derivative will be the slope of the tangent line at a particular, so we're just finding the derivative function in another way. And so what we want to remember for this case is that the derivative d over dx of x to the n is equal to n times x, n minus 1. So for an example, if I say, 4x, x squared, well, the derivative of that is just 2x and then 2 minus 1, which is 1. So that's just 2x to the first. So same rule applies here, but also we want to remember another rule, which is that 2 times, or sorry, not 2, but any constant times f of x is actually equal to the constant times the derivative, and then of f of x, if that makes sense. Constant times the derivative of f of x. So we're just going to do that here in a linear fashion. So we'll say 2 times 3, again, the derivative. But also, I think another point which could help illustrate this further is that the derivative of f of x plus h of x minus g, or plus h of x minus g of x is actually equal to the derivative of f of x plus the derivative of h of x, and then minus the derivative of g of x. So it's like you're breaking that derivative down. So we'll take the derivative of this, take the derivative of this, and then take the derivative of this. But also another thing to remember is that the derivative of a constant is 0. Okay, because if you think about a constant, right? Like if I had a constant, like let's say 4. If I do f of x equals 4, this is what my graph would look like, and that's constant. And we know that the gradient at this point would be of a horizontal line, at least, would be 0. So the derivative of a constant is 0. So these points are to be remembered while solving this question. So we'll say y prime of x equals 2 times the derivative of x to the third minus the derivative of x squared plus the derivative of 2. And we are going to apply this law. So we're going to say 2 times 3x squared. We're bringing that constant down, and then we're decrementing the power by 1 minus 2x. 2 minus 1 is 1. So plus the derivative of a constant is 0. This becomes 6. This becomes 6x squared minus 2x is what the derivative is. So y prime of x is equal to 6x squared minus 2x. And this is, this is our derivative. This is our derivative function, if that makes sense. This is our derivative function. And we can plug in any x value into this derivative function. And what we will do is that, if you look at y of x versus y prime of x, what is the purpose of y of x? The purpose of y of x is you put in any x value and it will give you it will essentially, it will return back a y value. And by that, you'd have an ordered pair. But for y prime of x, you plug in an x value and you're going to have the derivative or the slope of the tangent line at that point. So, both of these functions work very differently in terms of what their input does correspondingly. So if I plug in my x value, which is this guy, an ordered pair is consistent of x and y. So if I put this ordered pair of x into y prime of x, I'm essentially going to have, well, what am I going to have, right? So if I do y prime of 1, right, y prime of 1, I'm essentially going to get, so y prime of 1 is 6 times 1 squared minus 2 times 1, which is equal to 6 minus 2, which is equal to 4. So the slope of my tangent line is 4. The derivative function is this guy. Y prime is this guy, or y is this guy. And then you can just you can do y minus y1 equals mx minus x1. And then you have your y, and then subtract from y1, which is 3, equals 4, and then x minus x1, which we know is 1. And so y minus 3 equals 4x minus 4. Y equals 4x plus minus 1, I want to say. That's the slope of the tangent line. Or that's the equation of the tangent line. This is the equation. This is the slope. This is the derivative function. And this is us plugging an x value into the derivative function to get the slope of the tangent line at a particular point. And that is that, yeah. So this is the next question here, and it's saying that the equation of a motion or the equation of motion of a particle is s equals t cubed minus 3t, where s is in meters and t is in seconds. So, I mean, what you can think about it is like, okay, s, like if you have, you know, a graph, like a graph, like this is s of t, right? And s of t equals the position, right? And this is equal to time. So before, where we had, you know, x and y, or, you know, y or f of x rather, in this case, it's just s of t. In this case, it's just time. So we're just changing our variables on our axis. And if this were any function, right, s of t gives us the position, but the first derivative, s prime of t, would essentially give us the velocity. So if we take the derivative of this, we're going to get the velocity. And again, if you want to take derivatives using one thing, if you want to take derivatives using the limit definition of the derivative or differentiation rules, both can get you to the same answer, but differentiation rules are a lot faster. F prime of t is equal to v. And then, so f prime of t is equal to v of t, it's equal to the velocity. But if you take the derivative of the velocity function, then you're essentially going to get, a of t, which is the acceleration, which means that s of t gives you velocity, and s prime prime of t, which is the second derivative of s, will essentially give you the acceleration. Okay. So with that in mind, it says find the velocity and the accelerations as functions of t. So what we will do in that case is we'll take the first derivative of s, and we'll then take and that will be our velocity, right? Because the first derivative is velocity. And then the second derivative of s would be a of t, would be the acceleration, right? So velocity, right? We'll say we'll say that v of t, v prime of t, or we'll say that this is part A, v prime of t, or not v prime of t, but just v of t, the velocity, is equal to s prime of t, which is just taking the derivative of this. And if you remember differentiation rules, f of x minus g of x is just the derivative of f of x minus the derivative of g of x. And then you also have a power rule, which states that, you know, if you have anything raised to a power, drop that power down, decrement the exponent, and then you're fine. So what we'll do in this case is we'll say that v of t equals s prime of t, and s prime of t will equal the derivative of t3 minus 3t, or t cubed, which is 3t squared. Again, bring that down, decrement the exponent, minus 3. The idea behind, so why did I say the derivative of 3t is 3? Well, the idea behind that is, like, you know, I have something of the form d over dx of 3 times, or of a constant, which in this case is 3, multiplied to a function, which in this case is t. And so that's equal to the constant multiplied by the derivative of f of x. And the derivative of f of x would just be like 3, that's the constant, times f of x, the derivative of t. Well, what would you find? What's the derivative of t? Well, t, you know that there's an implicit 1 here. And so when you bring that 1 down, you get 1t, and then 1 minus 1, 1 minus 1 is 0. So 1 times t to the 0, we know that anything raised to the 0 power is just 1, so that's just 1 times 1. So then if I were just to do 3 times the derivative of t, which is 1, it's just 3 times 1, which is why I said that the derivative of 3t is just 3. 3t squared minus 3. And at this point, so this is, this is your derivative, right? V of t is equal to 3t squared. And then, a of t, which is the acceleration function, is equal to s prime prime of t, which is just the derivative of the derivative. So that's just d over dx of the derivative, which is, in this case, 3t squared minus 3, which would just be 3 multiplied by 2t minus 0, because the derivative of a constant is 0, which is just 6t. So this is part A. And we'll conclude with the fact that v of t is equal to 3t squared minus 3, and then we'll say that a of t is equal to 6t. And then it says, the acceleration after 2 seconds. Well, we have a function that allows us to input time. And then once we input time, we can essentially just get the acceleration at any given moment, because this is the acceleration function. So part B is just saying that a of t is equal to 6t. So if I do a of a particular time, let's say 2 seconds, then I'll get 6 times 2, which is 12 meters per second. That's part B. Part C essentially just says that the acceleration when the velocity, what is the acceleration when the velocity is 0? Well, it's saying that, this is defined as your, actually, what it's actually asking for C is what is the velocity, or actually what is the acceleration when t is equal to 0? Or when, so it's, let me go ahead and pull up the correct question. So it's asking us what is the acceleration when the velocity is 0. So if you want to find when the velocity is 0, so this is part C. If you want to find when the velocity is 0, just take the velocity, what the velocity function is defined as, and set that equal to 0. That's 3t squared equals 3, and then t squared equals 1. And then we take the square root of both sides. That's t equals plus or minus negative, plus or minus 1. Time can never be negative, so t equals 1. So when the velocity is 0, t is equal to 1. And then, so it's saying that when the velocity is 0, what is the acceleration? We'll just take, so when the velocity is 0, time is equal to 1. So just take time and plug it into the acceleration function, 6 of t, so a of 1, and that is just 6. That's part C. And that concludes part C, or really the question in its entirety. So for this question, it's essentially telling us to find the derivative and then plug an x value of 1. Well, really what it's saying is find the second derivative. That's what this notation means. It says, if it were like this, find f prime of x, or f prime of 1, it would just be saying find the first derivative. Just take the derivative of this once and then plug in 1 into the derivative. But in this case, it's saying find the second derivative. So take the derivative, and then so basically do d over dx of f prime of x, right? So find the derivative and then take the derivative of it again. if that makes sense. So we'll find the first derivative, and then we'll find the second derivative, and then we'll plug 1 into the second derivative is what this means. So f prime, right? Let's start with f prime. The idea behind this is that if you have f of x over g of x, this is basically what this is the derivative of f of x minus multiplied to g of x minus the derivative of g of x minus f of x. Or sorry, it's multiplied by f of x all over g of x squared. This is the formula that we're going to use. So we're going to say that f prime of x is equal to x squared. So it's the derivative of the first guy, f of x, which in this case is x squared, multiplied by 1 plus x minus the derivative of 1 plus x multiplied by x squared all over g of x squared, which in this case g of x is 1 plus x. So we're going to say 1 plus x squared. So you can see that we had f of x, we had g of x, f of x times g of x, f of x times g of x, and then minus g of x times f of x, g of x times f of x over g of x squared, g of x squared, g of x squared, g of x, and then squared. That's the idea. And we'll continue on with this. And one thing I do want to add is that, like, if you had a minus b over, I don't know, h, this is the same thing as a minus b multiplied by 1 over h, right? So we can definitely get rid of this part here and just do this whole thing multiplied by 1 over h. Now we'll take the derivative of this, which is a application of the power rule, which is 2x multiplied by 1 plus x minus the derivative of this. This is 1 plus x. Derivative of constant is, so when you have this and this, take the derivative of them both, right? F of x plus, the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. So take the derivative, this is, the derivative of constant is just 0, the derivative of x is just 1, because x, you have d over dx of 1. There's an implicit 1 here. And if you drop that 1 down, you get 1x, 1 minus 1 is 0, or 1 minus 1. Yeah, you decrement the power. This is 1 times x 0, and this x of 0 is just 1, so it's 1 times 1. And then that's why the derivative of x is just 1. But the derivative of a constant, right? So if you took the derivative of a constant, it's just 0. I think, you know, if you put the 1 down, 1, and 1 of 0. I don't think, I mean, I'm sure it has an algebraic reason for it, but the derivative of a constant is 0. That's just 0 plus 1 times x squared, which is just 1 times x squared, which is just x squared over, or in brackets, 1 over h. This comes about to being 2x plus 2x squared minus x squared over h, which comes about to being 2x plus x squared over h, which means the first derivative, f prime of x, is equal to this. But of course, our work is still about us where, oh, why did I put over h? I think I was too confused. I was doing the whole limit thing. Idea here is that it, you know, in the denominator, you should have 1 plus x squared. So 1 plus x squared g of x. So in this case, our g of x is 1 plus x. So all these h's, I was too used to using the limit definition of the derivative. All these h's should be g of x squared. So g of x squared. And now that we have done that, now that we have the first derivative, we're going to hop on over and take the second derivative. So the first derivative is what? So we said that it was 2x plus x squared over 1 plus x squared, right? 2x plus 2x squared plus 1 over x squared. We said that was the derivative. And now we're finding the second derivative, which is going to be more tedious. Same idea. This is f of x. This is g of x. Same quotient rule formula. And we're going to apply that. So we're going to say that f prime prime of x is equal to the derivative of f of x, which in this case is 2x plus x squared multiplied by 1 plus x squared, which is multiplied by g of x. And then we subtract from the derivative, so d over dx, of 1 plus x squared, this time g of x, multiplied by 2x plus x squared. And we'll do that multiplied by 1 over g squared, g of x squared, whatever. Derivative of 2x is just 2 plus 2x, right? So we're taking the derivative of this and this. And then multiplied by 1 plus x squared, and then we're still finding the derivative of this. So this is 2 and then 1 plus x, the first power. If you're familiar with the chain rule actually comes about to being 1, so we don't have to elaborate. And then we'll say 2x plus x squared, 1 over g squared. So we did 2, 1 plus x multiplied by 2x plus x squared, 1 over g squared, 2x plus x, 2x, and then, yeah. We'd want to multiply this out, so we'll go off to the side and we'll do 1 plus x times 1 plus x. We'll say that this is 1 plus x plus x plus x squared, which is equal to 1 plus 2x plus x squared. So 1 plus 2x plus x squared multiplied by, or let me go ahead and move this out to the right a little bit. 2 plus 2x times this minus, so 2 plus 2x, right? 2 plus 2x, 2x plus x squared, multiplied by 1 over g squared. We'll get this out of the way. And what we'll do at this point is we'll say we're going to multiply through. We'll say 2, so 2 plus 4x plus 2x squared, 2 plus 4x plus 2x squared, and then plus 2x plus 4x squared plus 2x cubed, interesting, minus all of what we had in here, which we'll actually have to elaborate on. We'll say that's 4x plus 2x, 4x plus 2x squared, 4x plus 2x squared, plus 4x squared, and then plus 2x cubed. And then that is multiplied by 1 over g squared, which comes about to being 2 plus 4x plus 2x squared plus 2x plus 4x squared plus 2x cubed minus 4x minus 2x squared minus 4x squared minus 2x cubed, and then of course 1 over g squared, and then 2x cubed cancels out with 2x cubed, minus 4x squared cancels out with 4x squared, minus 4x cancels out with 4x, minus 2x squared cancels out with plus 2x squared, and you're left with 2 plus 2x over g squared. What was g in this case? Coming back to what we were actually taking the derivative of, which was 1 plus x squared, which means 1 plus x squared was our g, and then squaring that, well, 1 plus x squared was our g, and then squaring that, so 2 plus 2x over 1 plus x, and then that is to the fourth. We multiply the powers, factor out the top, so 2 is common, 1 plus x over 1 plus x to the fourth, and that is just 2 over 1 plus x to the third, because this cancels out with one of this. Hence, in conclusion, f prime prime of x is equal to 2 over 1 plus x cubed. And you know, if you plug go to Mathway real quick, get it out of the way here. If you say that, you know, f of x is equal to, I think it was 2 over 1 plus x, 2 over 1 plus x cubed, Jesus Christ, 2 plus 1 plus x cubed, and for x equals 1, evaluate the function, you get 1 over 4, which means that the f prime prime of 1 is 1 over 4. This question wants us to find the slope of the tangent line, or not the slope, but really the equation of the tangent line. We'll write this so that it's a tad bit bigger. We'll say that y equals e to the x cosine of x plus sine of x, and we'll get rid of that. Oh, right, of course, at the points 0, 1, and we'll get rid of this. Slope of the tangent line. So for the slope of the tangent line, we first need the derivative of y prime, or we need the derivative of y, which is y prime, and that would symbolize m, and m is the slope for the tangent line, and then we'll use m to find the equation of the tangent line. Y prime is equal to the derivative of e to the x cosine x plus sine of x, which this is a product rule. Product rule states that if you have the derivative, well, actually first, these are two different functions, right? So we can separate this d over dx, e to the x cosine x plus the derivative of sine of x. And when you do this, this is an application of the product rule. So the product rule states that the derivative d over dx of e, or sorry, not e, but but f of x multiplied to g of x. So the idea here is that e of x is one function, cosine of x is another function. So the idea is that you do this is the derivative of this of two functions multiplied together is not the derivative of the two functions independently and then multiplying them. It's actually the derivative of the first function multiplied to the derivative of the second function added to the derivative of the second function multiplied to the derivative of the first function. Let me make that a little more clear. It is the derivative of the first function, f of x, multiplied to the derivative of g of x, added to the derivative of g of x, multiplied to the derivative of f of x. So in this particular case, we would do the derivative of e of x multiplied to the derivative. It's just multiplied to cosine of x plus the derivative of sine of x. So you want to remember that the derivative of sine of x is actually equal to cosine of x. So the derivative of this is just cosine of x. Well, okay, sorry, I think I'm getting too ahead of myself. When we're doing the product rule derivative, which is here, we're doing the derivative. If you look back at the formula, it's the derivative of the first function multiplied to the derivative of the second function, derivative of the first multiplied to the second function, and then you do the derivative of the second function multiplied to the first. Right? And then that is plus the derivative of sine of x, which is cosine of x. Derivative of the first multiplied to the second, derivative of the second multiplied to the first, plus the derivative of this guy. The derivative of e to the x, so we know that the derivative of sine of x is just cosine of x, and you also want to remember that the derivative of cosine, or not cosine, but e to the x is just e to the x. So what is the derivative of e to the x? It's e to the x multiplied to cosine of x plus the derivative of cosine of x. You want to remember that the derivative of cosine of x is equal to negative sine of x. Derivative of cosine of x is equal to negative sine of x. Multiplied by e to the x plus cosine of x, which is the derivative of sine of x. And then it would just be e to the x cosine of x minus sine of x, e to the x plus cosine of x. And this is the slope of our tangent, or not, well, this is the derivative function, okay, which means y prime equals this. So we can plug in any x value and we'll figure out what the slope of the tangent line is at that point. So in this case, we want to plug in an x value of 0. So we'll take 0, e to the 0, cosine to the 0, minus sine to the 0 multiplied by e to the 0 plus cosine of 0. And e to the 0 is 1 because any variable to the 0th power is 1. Cosine of 0 is 1. Minus sine of 0. What is sine of 0? What is the y value at 0 degrees on the unit circle? Well, it's 0. Times 1, which is 0, plus 1. So you have 1 minus 0 plus 1, which is equal to 1 plus 1, which is equal to 2. And then we can say y minus y1 equals m, x minus x1. Y in this case, or y1 is 1, equals m, which we know is 2, x minus x1. So y minus 1 equals 2x minus 2 so x1 in this case was 1. So minus 2. So y equals 2x. If I add 1 to both sides, I'll get minus 1. That is the derivative. That is this equation of the tangent line. So this concludes this particular question. And that is pretty much all